Good evening, friends. Study with Apala. Chapter 2, The Earth. New methods. Radioactivity in the 20th century. The problem of the age of the Earth has been dealt with considerable success by methods based on radioactivity. It was a French physicist Becquerel who discovered in 1895 that nuclei of a certain element are inherently unstable and are actually in a process of spontaneous disintegration at a constant rate to form stable and product. Subsequent studies by numerous scientists, chief amongst whom were Marie Curie, Pierre Curie, and Rutherford, but radioactivity on firms foundations as a subject of a great practical importance in numerous fields. In geology, numerous workers applied this science for determining the age of the earth for period of over 30 years and from 1905 to 1939 and obtains valuable data. Principles. The radioactive methods for the determinations of age of the earth are based on a simple application of a theory of radioactivity. Supposing a rock samples obtained from any part of the crust of the earth contain a radioactive element A that has been spontaneously decaying at a fixed rate to the end product element B. Obviously, it will also be containing some amount of the end product B. The change is akin to a chemical reactions of first order and can be represented by the relationship capital A arrow B. Even evidently, if a relatives amount in terms of atoms of element A and B present in the same sample are precisely known, and the rate of radioactive decays of A to B is also known. Thence the times that has elapsed since the formations of the radioactive substance, and hence the age of the rock containing that element can be calculated. Disintegrations consonant lambda. So Rutherford framed a simple law on rate of radioactive disintegrations which state that a certain constant fractions of any sample's radioactive element undergoes a change in a unit time. In radioactive determinations of age of the earth, the concept of disintegration constant, also called decay constant, is of fundamental importance. It is divided as follows from the systems A and B, A to B. And so let the original numbers of atoms is in A at the time of start of decay is equal to n0. Let the times that has elapsed since the beginning of decay is equal to small t. Let the numbers of atoms present after intervals small t is equal to n capital. Then the rate of change dn dt is equal to lambda n, or lambda dt is equal to dn upon lambda, n dn upon n, where where lambda is the disintegration constant. If t is equal to 1, so then lambda is equal to dn upon n. From the above relationship, lambda may be defined as the fractions of total number of atoms of the radioactive substances A at any time which disintegrate as a second. Obviously, lambda is a constant only for a particular radioactive element. It is independent of the original amount of the substance. Further, any physical or chemical change occurring on the rock containing the radioactive element have no effect on this integrations constant. The rock containing both element A and the end product B, the parent and daughter of radioactive pairs, their amounts being known previously, will have a minimum age given by T as per following relationship. T is equal to 1 by lambda in B plus 1 upon A, where T is generally given in millions of years. Half-life. It has been observed that the rate of disintegration of radioactive element so considerable variations from element to element. In some elements it is so fast that they decay completely. In matter of a minute and seconds, whereas in others the radioactive decays take place in inconvenience livable in conceivable slow rates. It may take millions of years for a constant fractions of a radioactive element to decay to a stable end product. It has been therefore found convenient to express the times required for decay of one half fractions of the original substances as a standard unit. This time is termed as a half-life period and has a constant value for each radioactive element. It may range from a few seconds to many millions years in different radioactive elements. It is expressed as a T half. Table 2.1 gives half-life periods of a few well-studied radioactive elements. Half-life periods of fused radioactive element radioactive pairs: uranium 238 to Pb, lead 206, uranium 200. Means this half-life period 4.5 into 10 to the power 9 years, uranium 235 to lead Pb 207.71 into 10 to the power 9 years, thorium 232 to lead 208 1.39 into 10 to the power 10 years, rubidium 87, strontium 87 4.7 into 10 to the power 10 years, chromium 40, argon 40 1.3 into 10 to the power 9 years. Thank you. Like, support and subscribe this channel.